Okay, so now we're going to look at the graphs of these trigonometric functions. So like I've been saying, we're just kind of dipping our toes into trigonometry. So we're not going to really go over all the graph properties. So we're just going to look at them on the graphing calculator and kind of talk about them a little bit here. So we'll start with sine. Sine is kind of like the default function that we like the most. So this is usually the one we look at first. So notice the unique shape of this graph. Okay, if we zoom out, it looks like a wave, right? It's going up and down and up and down, and we can kind of see exactly that circle being reflected, that from here to here, which is 2 pi, it actually is labeled as 2 pi. We go through these unique values, and then we come back to that 2 pi where the values start to repeat because we've gone around the circle one time. And then we would just do it again until here we get to 4 pi, right? Okay. And in the other direction, if we go backwards on the circle, it would be reflected as negative numbers. Here would be the negative 2 pi. Okay. So you can see sine of 0 is 0. That was one of the values we looked at. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. That's 270 degrees. And then sine of 2 pi, we're back at 0. So it is a wave. So like in physics or whatever subject, whenever you're looking or trying to model anything that is a wave, like sound, light, that kind of stuff, right? These trig functions are going to be there. Okay. Let's look at cosine now. Cosine looks very similar. It just starts kind of at a different place, right? It's starting at 0, 1, and then it's going through all the values, and then at 2 pi, we're back up at the same values, right? So this is what we would call one period of cosine, going from 0 to 2 pi here. And we can see the other values along the way here. Pi negative 1, pi over 2, 0, 3 pi over 2, 0. Okay. So these are very similar graphs. In fact, they're actually the same graph, just shifted over. If you just shift over sine by pi over 2, it is the exact same graph. And if we overlay them on top of each other, it's pretty easy to see that, we just, if you just shift the sine graph, the blue one here, to the left pi over 2, then this is the exact same graph, right? So in other words, sine of x plus pi over 2 is equal to cosine of x. Okay, that's another identity with the trig functions. So very similar graphs, very similar properties. We're actually going to see when we talk about derivatives in calculus that the derivative of each of these graphs is the other graph. In one case, it's the negative of the other graph. The derivative being the slope of each of the graphs. So that's another interesting property that we'll see. So what about some of the other ones? Tangent, for example. Well, tangent is the ratio of sine and cosine. So it's going to be pretty different, right? We're introducing fractions here. With fractions, we naturally have asymptotes, right? We actually have a whole bunch of vertical asymptotes. Let's go ahead. Let me just bring up the sine and the cosine one more time here. Oops. If we think about tangent as the ratio of sine to cosine, that means whenever cosine is 0, the tangent graph is going to be undefined. So you can see that being overlaid right here. At pi over 2, when cosine is 0, the tangent graph is undefined, so we have a vertical asymptote. Okay, so it's going off to infinity and off to negative infinity. And then same over here. So every time cosine hits that x-axis, we get this vertical asymptote here. Okay. Um, let's see. What else can we say about this? So that, yeah, this tangent it's a little bit unique here. Its range is negative infinity to infinity. Its domain is all real numbers except for all the multiples of pi over 2. It's a bit strange, right? Not all the multiples. We could write it out, but basically pi over 2, 3 pi over 2. So you would write pi over 2 plus or minus pi times k. So if you add pi over 2, if you do pi over 2 plus pi, you get 3 pi over 2, right? In other words, you go halfway around the circle. So that's how we'd write that. And by the way, the domain and range of cosine and sine are all real numbers. The domain of cosine and sine are all real numbers. The range is -1 to 1 for both of them, right? Included. So now if we look at some of the other functions, so let's overlay sine and cosecant. Right, remember cosecant is 1 over sine. So you can see how these functions work. Again, at 0, when sine is 0, we're going to have vertical asymptotes. So all these places. So these are kind of some strange graphs. They look like kind of like alternating parabolas. So yeah, so they don't get a lot of use, but they're kind of just interesting to look at based on, so they're the reciprocals of the sine functions. And then same thing with the cosines and the secant functions, right? Pretty much the same thing, just move everything over a little bit. And then finally the cotangent. It's 1 over the tangent functions. So as tangent is 0, we get vertical asymptotes at the cotangent. So tangent is the blue functions here. Cotangent is the red functions. So you can see whenever the blue line is getting to 0, we have a vertical asymptote here. Let me take that one off to make it a little easier to see. So it's basically just, it looks a lot like the tangent graph, just kind of backwards, right? So, but anyway, we'll kind of study the graphs of the sine and cosine a little bit when we look at calculus a little bit, because just a lot of examples in calculus use these functions. Because like I said, one of them is the derivative of the other, which means the slope of the other. So they kind of have some nice properties because of that. But yeah, but we don't use them. We just don't use trig a lot in statistics, so we're not going to focus on them too much. But yeah, they're good to kind of have for some examples and just to have in our back pockets for just a couple of times where it does end up coming up in trig, because it does come up in some probability distributions that are important in trig.